This lecture is about tests of joint hypotheses. This is page 2 of lecture note 7. So now we are going to test hypotheses about multiple coefficients. Before, we've only tested hypotheses about a single coefficient, beta 1 or beta 2, for example. Now we're going to test hypotheses about more than one coefficient at a time, beta 1 and beta 2, for example. So we're kind of jumping into the section of the class where we start talking about how to select the appropriate model. You now know how to run a regression. You know how to write down a single variable and multiple variable model, and you know how to estimate those models in R. You could figure out how to do it in Excel if you Google it, I'm sure. So you've got some regression experience under your belt, but now we want to talk about what is the right regression to run. Do we just run anything we can think of? Do we throw all the variables in the model that we have data on? Or do we select the variables with some kind of, is there some reason for selecting specific variables? So this is going to be tests of joint hypotheses, which is going to help us select which variables are important. Okay, so let EXPN be the expenditures per pupil. So I'm right here. Let expenditures, EXPN be expenditures per pupil. Our population regression model now has 3 regressors: student-teacher ratio, expenditures per pupil, and the percent English as a second language learners in the class or in the school district. We're still, our dependent variable is still test scores, so we're still trying to figure out how each of these variables influences test scores on average in a school district. Now our null or joint hypothesis is that school resources, so school resources being basically money at a school, matter versus they don't matter. So what are school resources in this model? School resources in this model are student-teacher ratio and expenditures. Expenditures being the amount of money the school has per pupil. So we want to find out, do school resources matter at all? So our null joint hypothesis is going to be that beta 1 0 and beta 2 0 equals 0. So both of these equal 0, not just one of them, but both of them simultaneously equal 0, versus the alternative hypothesis that one of them, the beta 1 does not equal 0, beta 2 does not equal 0, or both. Couple notes: a joint hypothesis will have Q restrictions. In this case, Q equals 2 because we have beta 1 and beta 2 that we're specifying our hypothesis about. If we had a joint hypothesis about all 3 coefficients in the model, beta 1, beta 2, and beta 3, then Q would equal 3. So why can't we just use regular t-tests on beta 1 and beta 2 and then decide if each of them is independently significant? So what we did in the previous set of lectures. Well, the answer is because beta 1 and beta 2 are not independently distributed, so we cannot look up their joint significance on a z-table. So the solution is to use a different test to test the significance of beta 1 and beta 2 at once. And so we're going to introduce the F-statistic. The F-statistic for joint hypotheses of about 2 coefficients is given in the following equation here. This is the F-statistic. It's equal to 1/2 t1 squared plus t2 squared minus 2 times rho t1 t2 times t1 times t2 over 1 minus rho squared t1 t2. Okay, so what are all these values? Where rho hat t1 t2 is an estimate of the correlation between t1 and t2, or this value here, the correlation between t1 and t2. Okay, but what are T1 and T2? T1 and T2 are the t-statistics from independent tests of significance about beta 1 and beta 2. So if you had beta 1 and beta 2, and you had the correlation between the two, you could plug those into this equation here. The t-statistics come from the general regression output, and the correlation is going to come from the error matrices, which you would learn about in a graduate course. So another note, the F-stat increases as either T1 or T2 increases. So you can see that as the what's going to cause the numerator in the F-statistic to increase? Well, T1 and T2, any increase in the t-statistics or the independent significance of either of those coefficients is going to increase the F-statistic. So when we reject our null hypothesis, when we wrote it down, we had the alternative was that beta 1, beta 2, or both are not equal to 0. So if we reject our null hypothesis, it could be that one of these is equal to 0 independently, but the other is statistically significant enough that it means that both coefficients are jointly statistically significant. Okay, so if we have a special case when T1 and T2 are independent, that means that the correlation between the two is equal to 0. So these terms, rho hat, drop out. So then we're just left with, this. F is approximately equal to 1/2 T1 squared plus T2 squared. So remember that t-stats have a standard normal distribution, or in other words, t-stat is distributed normal 0, 1. So then in large samples, the distribution of the F-statistic is the average of two normal random variables, or basically the sum of two normally distributed random variables. And luckily we have a distribution that is the sum of two normal random variables. It's called the chi-squared distribution. I'm giving it to you in rainbow here, so hopefully you remember it. It's a chi-squared distribution is defined as the distribution of the sum of q independent standard normal random variables. Perfect for this situation. And therefore the F-statistic has a chi-squared distribution with q degrees of freedom. Okay, so how are we going to use this? Well, we're going to use it by just the R is going to estimate F-statistics for us, and then we can compare that to chi-squared tables. So let's have a test of a joint hypothesis above. Now that we know what the test is going to be, our joint hypothesis was that beta 1, 0 and beta 2, 0 are both equal to 0. Now let's test it. Suppose we estimated the model, and our F-stat was 5.43. So what's our rejection rule in this case? It's not 1.96 because we're not dealing with a standard normal distribution. We're dealing with a chi-squared distribution. So our F-statistic is going to be based on the chi-squared table. So let's look that up. Here's the chi-squared table. So we have 2 degrees of freedom. Here's 2 degrees of freedom. Or 5% significance here, or 95% confidence. There's going to be a value of basically 6. And then we want to, we're going to end up dividing by 2 because that's our degrees of freedom. So our critical value is then going to be 3. So we want to compare our F-statistic to 3. Okay, so the F-statistic, the critical value, I should write this down on here. The critical value for an F-statistic, so the critical value for the T-statistic for 95% confidence was 1.96. So the critical value here for the F-statistic is the chi-squared distribution divided by q. In this case, we looked up the chi-squared distribution, we find it was for a 5% significance with 2 degrees of freedom, it's basically 6, and we divide by q, so divide by 2, it's basically 3. So our rejection rule is 5.43 greater than 3. It is, so reject the null, and at least one of the regressors in the model is significant. So at least one of those variables, student-teacher ratio, let's go back up and look at it. We estimated this model here. At least one of these variables for school resources is important, if not both. We know that. So essentially we're saying school resources do matter. Okay, so that's the F-statistic. Now, how else can it be useful? It can be useful to help us determine what's the best model to be working with. Suppose you have a model, and just a generic model now, of y equals beta 0 plus beta 1x plus beta 2x plus beta 3x. We're going to have a hypothesis that beta 2 and beta 3 are equal to 0, versus an alternative hypothesis that beta 2 does not equal 0, beta 3 does not equal 0, or both. Now, what is the point of this hypothesis? Maybe our variable of interest is x1. That's the one we're really interested in. We want to know, does x1 affect y? And we think x2 and x3 might be important control variables. So let's test two different models. Let's test the large model. We'll call this model 1, the large model, versus model 2, a smaller model that doesn't have x2 and x3 in it. It only has x1. So this joint hypothesis about beta 2 and beta 3 is going to help us decide which is the better model. The hypothesis suggests that the better model is actually the smaller model with only x1 in it. So if we reject the null, the larger model is better. In other words, if we reject this null hypothesis up here, if we reject that beta 2 and beta 3 are equal to 0, that means that they're not equal to 0 with 95% confidence, and x2 and x3 are important variables to have in our model. They do have an effect on y. So if we reject the null, then the larger model is quote-unquote better, and the r-squared, adjusted r-squared, should be higher than model 2, which doesn't include them. If we fail to reject the null, on the other hand, then the smaller model is probably okay. So if we fail to reject the null hypothesis, and we find that beta 2 and beta 3, beta 2 does not equal 0, beta 2 and beta 3 might equal 0, we fail to reject that null hypothesis, that would suggest that x2 and x3 really have no effect on y. We should probably check the t-stats on each of those coefficients as well. Make sure that neither of them is independently significant. But if we fail to reject this joint hypothesis, then that's one piece of evidence that maybe model 2 is sufficient for our purposes. Why might we only want model 2? The more variables we add to the model, the less precise our estimates of beta 1 are going to become. And beta 1 is the coefficient of interest if x1 is the variable that we care about. Okay, so the other thing that you get when you estimate a model in R, a regression, is you get an F-stat that is the significance of all the variables in the model together. So let's see what we get when we look at R. So I have the data up from problem set 4, the beer data set. I'm going to estimate the large model here with all the variables in it. We have the quantity of beer regressed on the price of beer, the price of liquor, the price of the other, and income. So that's linear mod 3. I'm going to run that. Then I'm going to summarize linear mod 3. What do I get? I get the intercept here is equal to 8.216 with a standard error of 1.796. Each of those with e to the 0.01, t-value 4.574, so that's significant. This one's significant as well. It's greater than 1.96. This one is not necessarily significant, depending on your critical value. For 95% confidence, it's not significant. This one is significant, and this one is significant as well. So we also have our residual standard error, basically the standard error of regression. The multiple r squared and the adjusted r squared. You can see the adjusted r squared here is lower than the multiple r squared, as we talked about in the adjusted r squared video. Always has to be less than or equal than the multiple r squared. And then we also have the F-statistic. I promised we'd talk about this. The F-statistic, which is the test of the joint hypothesis that all of these coefficients are equal to 0. And we're going to reject that most likely, as long as you have at least a reasonably well-specified model. The coefficients are going to be, we can reject it. None of them matter.